In chapter 2, we're going to be looking at limits of functions. So this first section is, we're just going to go over the definition of the limit of a function. And we're actually going to go over quite a lot of examples so we can, read and then digest this idea of a limit, right? Because this notion of limit of a function pretty much underlines the study of calculus, right? So when we fail to understand that idea, our study of calculus becomes, just a drudgery and we're just juggling formulas. But before going to continuity and differentiation and integration, we need to know or understand limits. So that's why we're going over limits in this chapter. And the last chapter about sequences is useful, and I'll mention why in this lecture. But we'll be using sequences in this chapter as well. So with that said, we go on to the first slide. So to build some intuition first, I'm not going to state the definition of a limit first. Take, for example, this function. Well, this function, uh, let me do this is difference of squares, right? So it's x plus 1, x minus 1 at the top, x minus 1. But it's not defined for what value of x? For x equals 1, right? It's not defined for x equals 1. So it's not equal to 1. So this is what the function looks like, right? Because if you cross those out, then we have x plus 1, the linear function, which we have in red. And that point I put here is just because we're going to define that point, f of 1 as 6. Now, remember, there is a missing point. Let me find my pen. There's a missing point right there, right? Because x can't be 1, so there is no value for f of x equals when x is equal to 1. So we're just defining it as 6. The reason I'm doing that, instead, like you might think, why don't we just define it as f of 1 equals to 2? Well, I'm just defining it to make a point. In this case, to take the limit, if you've seen in calculus, as x approaches 1, we know the limit exists, right? Maybe you, in calculus, you used a technique where you use both your fingers and see where they touch. But here we're going to define it rigorously. And if you remember calculus, well, then you know there is a limit at 1, which is 2. But in this case, this point up here, 1, 6, this ordered pair, doesn't really change the limit for us. So we don't really consider that point, right? So we're going to define the limits. We let the function from d to r with x not an accumulation point of d. Then f has a limit L at x naught if and only if for each epsilon greater than 0, there is a delta greater than 0, such that if 0 is less than the difference between x and x naught, and it's less than delta, where x is in D, then the difference between f of x and L is less than epsilon. So probably like the convergence definition, there's a lot to unpack here. And well, we should know it's incorrect for us to just memorize all the definitions, just as this one. Just because we don't want to get things out of order when rewriting it, we should really, unpack and kind of examine, dissect it, and fully assimilate what these things actually mean. So first, for instance, is that x naught is an accumulation point of D. Now, here I should mention, we're going to do D is going to be a subset of the real numbers, right? We're just choosing a subset of the real numbers, D. So for example, in this case, D could be from -2 to 4. This interval can be D. or it can be any other subset of the real line. So x naught is or has to be an accumulation point of D for our definition to even apply. Now here, epsilon is the desired degree of closeness, right? Chosen in advance. And to fulfill that definition, this definition, we must find a delta greater than 0. Which usually depends on, or actually, which generally, yeah, depends on epsilon. But such that if x is in our neighborhood, right, then f of x, that should be element of, if this, then this. F. And what may help with us here is a visual, kind of like a limit of what this definition even means. So let me just erase this. So what does the definition tell us? That for a given strip here, a neighborhood centered at x naught, which is an accumulation point, well, that if our point lies anywhere in here or in here, actually, let me use a different color. Let me use green. If our point lies anywhere in here, right, and it keeps going, or in here, and it can get arbitrarily close to x naught, then our L should lie anywhere here. Our difference between f of x minus L should be in this neighborhood. That's what this means. It's kind of like the, well, yeah, that's how we define the limit. So how do we prove, using this definition, how do we prove that x squared minus 1 over x minus 1 does actually have a limit at x equals 1? Let's see. And in these slides, because the definition of a limit is new, I will be putting them on each and every one so that it can remind us of the definition, so we don't have to go back to another slide and just keep looking at the definition over and over again. So here I present the definition of a limit again. And now we're going to prove that x squared minus 1 over x minus 1 has this limit at x equals 1 here. And can you guess why I have 2 there? Well, if you plug in 1, x plus 1, x minus 1 over x minus 1, these cancel out. X plus 1 is equal to 1 plus 1, so that's why we get 2. So that's why we're guessing that the limit is 2 here. Right, so we're going to choose epsilon greater than 0 and choose, in this case, it's a linear function. So we should guess that epsilon is going to be equal to delta to obtain a neighborhood. Sorry, and it's of slope 1. That's why we choose epsilon equal to delta. So to obtain the neighborhood, 1 minus a delta neighborhood around x naught, sorry, around x, which is 1, we have this here. So this is the delta neighborhood centered at 1. Well, we have to choose a neighborhood of 1 such that for x in this neighborhood with x not being 1, so any other point in this neighborhood, the corresponding point on the graph, meaning up here of f lie within this strip, an epsilon neighborhood around L. What we're guessing is 2, the limit being L. So an epsilon neighborhood around L. So this here is L minus epsilon, L plus epsilon. That's this neighborhood. Over here we have the delta neighborhood around X. So in this case, we have 1 plus delta interval to, 1 minus delta to 1 plus delta. Okay, well, if delta is greater than the difference between x minus 1, so if, again, we're just stating delta, the distance between x and 1, any point in here, is less than delta, and it has to be positive, well, that equals epsilon by our choice up here. So we carry out the definition. F of x minus L, which we're guessing is 2, is equal to x squared minus 1 over x minus 1 minus 2. And that just simplifies to x plus 1 minus 2, the absolute value of that, which is just equal to the absolute value of x minus 1. And we know that is less than delta because of this over here. And it's equal to epsilon. So it's showing if, just as the definition told us, if this is true that I'm circling, then this has to be less than epsilon, right? Which it is. So that's why we have a limit at x equals 1, which is 2. Now I don't expect it to kind of sink in the first time we're learning this. So we're going to go over more and more examples. We're not going to do much of anything else. So the next example, first I'm going to bring up the limit definition just to have a reminder. Our next example is the function f of x equal to absolute value of x over x, right? And we're not including 0 in the domain because it's not defined at 0. And here it says that when x is negative, f of x is equal to -1. When x is positive, f of x is equal to 1. To help you, again, we're going to include a picture here. So this is what the graph looks like. And here, from your skills in calculus, you would say that this function does not have a limit at 0. Because again, if you use your 2 fingers from the right and from the left, they don't touch at x equals 0, right? So now we're going to proceed to show that indeed it does not have a limit at 0. So first of all, we're going to choose epsilon equal to 1/4. And we're going to assume L is a limit of f at 0. We don't know what L is. We know it's a real number, but we don't know what it is yet. So to show that this is not a limit, we're going to do a proof by contradiction. Okay, so this means that there should be a delta greater than 0, such that if it's greater than x minus 0, then the difference between f of x and L should be less than 1/4, because that's what epsilon is, right? So this is epsilon. And I'll mention why we chose epsilon equal to 1/4. Just as the proofs in the sequence chapter, the sequences, a lot of the times it helps to work backwards, so we'll get there. Well, now we're going to choose P on the real line and Q to be negative delta over 4. So this, we know delta is positive, so this must be a negative number. P is less than 0, Q is greater than 0. Right? Q is delta over 4, so that's a positive number. So if P is a negative number, that means f of P must be -1, right? So this is -1, and P is positive, so it must be +1. So here it goes. The delta, choosing delta, P, Q, actually choosing P, Q, and epsilon is going to become evident with this next line. Then 2, which is equal to f of P minus f of Q. By the triangle inequality, that's less than f of P minus L plus L minus f of Q. And 1/4 plus 1/4, well, again, this here and this here, we don't know what L is. It could be anywhere here, right? This blue line is what I guess a reasonable guess would be of L. But that distance is 2, right? But here we're saying f of P minus f of L. If we're using the definition of a limit, well then they should be less than 1/4 plus 1/4. Why? Well, because f of x minus L over here, where it shows here, this needs to be less than epsilon for our definition to make sense, right? For our definition to apply. Remember, we need x minus x naught less than delta. That's an ugly delta. Less than delta for this to apply, right? So f of x minus L is less than epsilon for any x, right? So in this case, we're using P. So here we have P. So we know this is less than epsilon, which is 1/4, and this is less than epsilon, which is 1/4. That's why it's less than 1/4 plus 1/4, and that's equal to 1/2. So we're saying 1/2 is greater than 2, which makes us arrive at our contradiction. So this function does not have a limit at 0. So kind of try to see, try to use the reasoning for this proof on the last example and the reasoning for the other proof in this example to kind of see what's going on. I think that would be a good exercise. Okay, our next example. Here's a definition of a limit. And we're going to define f to be for the domain 0, 1, the interval, the open interval, into the R, into the real numbers, by f of x equals sine 1 over x. And we're going to see if f has a limit at at x equals 0. So a visual should help us here. So in this case, with this function, f of 1 over n pi is always equal to 0 for any positive integer n, and f of 2 over n pi is either positive 1 or negative 1 for n, an odd positive integer. And if you notice, the function oscillates more and more wildly as x becomes close to 0, right? So as we go from right to left, approaching 0, this function oscillates more and more. Okay, so we have our conjecture. F does not have a limit at 0. And if you remember in calculus class, when you have this bunch here, it doesn't have a limit or derivative, but we won't be talking about derivative for a while. But we know it doesn't have a limit. That's our conjecture. So let's prove that. We're going to let L be any real number. And we're going to choose epsilon to be equal to 1/3. I guess I'll tell you now, although it won't make much sense, but the difference between 0 and 1, if you make a 1/3 neighborhood around 0, this is a neighborhood around 0, and a 1/3 neighborhood around 1, they don't overlap at all. So that's why we're choosing 1/3. Keep that in mind because I know it doesn't make much sense right now. But let L be any real number and choose epsilon to be 1/3. Well, to show L is not a limit at f of f at 0, we need to show, it suffices to show actually that for delta greater than 0, there is, not us, there is an x in our domain such that x minus 0 is less than delta, but f of x minus L is greater than or equal to epsilon, right? It's not less than epsilon, it's greater than or equal to, which will destroy the whole definition, which will show that there is no limit at 0. So by choice of epsilon of 1/3, just as I was explaining up here with the neighborhoods, either 1 isn't in the neighborhood of L or 0 isn't in the neighborhood of L, right? Because those neighborhoods can't overlap. Now here we're just going to suppose that this one is the case. 0 is not in the neighborhood of L. Okay, well then given delta greater than 0, there's a positive integer n such that 1 over n pi is less than delta. And as we remember from up here, from the boxes, the black boxes, f of 1 over n pi is equal to 0, which we know is not in the L neighborhood. So therefore, just doing a little algebra, f of 1 over n pi, the distance between that and L, is greater than or equal to epsilon. Right, so if I could draw a visual, we have 0 here. I'm drawing on the graph now. I'm going to do it in red. If we have 0 here, we're guessing L is somewhere up here. And the neighborhood around L is something like this. Or we can maybe even include 1 for this sake. L and its neighborhood from here to here. Right? 0 is not in the neighborhood of L. So we can find an integer n such that this x value is less than delta. And this this function, plugging in that x to our function, will give us 0, which we know is not in our L neighborhood. Therefore, the difference between 0 and L is more than 1/3. Right? So therefore, f does not have a limit at 0. Okay, and our last example, again, the definition. Our last example is a function you're probably familiar with. We're going to define a function with the domain 0, 1, mapping to R, the real numbers, by f of x equals 1 over x. Okay, what does that look like? That looks like right here. This is our domain from red all the way to red. We're just considering 0 to 1. We shouldn't even pay attention to the rest. In fact, let me just trace over it. Okay, we're going to be looking at f of, actually at the limit point when x is equal to 0. So our conjecture is to say f does not have a limit at 0, right? Well, because remember, if you learn from calculus, well, it just goes to infinity, right? So It doesn't really have a limit. And again, we're going to show that that's true by showing that our definition cannot hold. Okay, so we're going to let L be any real number. Choose epsilon greater than 0. And the way we're going to choose epsilon is in a way such that L plus epsilon is greater than 0. That's going to come in handy later. And again, it's not just coming from divine inspiration, but it'll make things work. So that's why sometimes we have to work backwards. But now, if 0 is less than x, less than 1 over L plus epsilon, well then L plus epsilon is less than 1 over x, right? So that's why we chose this. That's why we chose that epsilon to fit this, so that we can have L plus epsilon less than 1 over x, which, well, is just equal to f of x. Okay, well that means that f of x minus L is greater than epsilon. Why? Just do simple algebra, right? Just move L to the other side, and now it's greater than epsilon. So if that's greater than epsilon, then its absolute value is greater than epsilon. So therefore, it's impossible to find a delta to fulfill the requirements of the definition. Right, so L does not have a limit point at 0, because wherever you think L's the limit, the closer we get to 0, the, I guess, more wild it's going to get, but the difference between one f of x and the other will increase, right? Because this just kind of like blows up, so to speak, as x gets closer and closer to 0. So no matter what neighborhood around x naught we choose, it wouldn't fulfill our requirements for the definition for delta, because of this fact that f of x minus L is greater than epsilon. So again, if it helps you, try using these reasonings for these proofs, for the four examples on each other. That's a good exercise to kind of get used to the limit, the definition of a limit. But again, just remember, it just means that for a certain strip in the x-axis, L should lie between an epsilon strip as well. That's pretty much how to say it informally, the limit definition. And hopefully we'll get more understanding about, or we understand better what a limit is in the next sections. We're going to be looking at the next section at limits of functions and sequences. So we're going to bring in sequences. And their algebra and so on and so forth. But again, make sure to read the definition of a limit, try to digest it, chew on it, and if it helps you, rewrite it, and then we'll work from there.